What if your iPhone, your Mac, and your Vision Pro could all talk to each other securely over any network without you having to build a single line of networking code? That is the promise of a brand new open source Swift framework called Loom. And in this video, I'm going to take you through everything it does, how it works under the hood, and whether it is actually ready for you to ship in a real app. Loom was created by Ethan Lipnik, the same developer behind MirageKit, which is a peer-to-peer screen sharing framework that lets you mirror your Mac display to an iPad or Vision Pro. MirageKit has been around for a while and has real users. Loom is essentially the networking engine that was extracted out of MirageKit and turned into a standalone general-purpose framework. So while the public package is brand new, the underlying code has been battle-tested in a shipping product. That context matters a lot when we talk about production readiness later. So what exactly does Loom do? At its core, Loom is a transport layer for Apple device-to-device communication. It handles 4 hard problems that every multi-device Apple app eventually runs into. First, discovery. How do you find other devices nearby? Second, identity. How do you know a device is who it claims to be? Third, trust. Should this device be allowed to connect? And fourth, reachability. What if the devices are not on the same network? Loom solves all 4. Let me walk through each one. Discovery is built on Bonjour, which is Apple's implementation of zero configuration networking. When your app starts advertising with Loom, it creates an NW listener under the hood. This is Apple's modern network.framework API, not the older Multipeer Connectivity framework. The listener publishes a Bonjour TXT record with metadata about your device, things like a protocol version, a device ID, the device type, the model name, an icon identifier, and even arbitrary app-specific metadata that you can define yourself. On the other side, Loom's discovery component uses NW Browser to scan for these advertisements. It maintains a dictionary of peers by endpoint and parses those TXT records into clean Swift structs. One important detail here is that both the advertiser and the browser enable a flag called include peer-to-peer. On Apple platforms, this activates something called AWDL, which stands for Apple Wireless Direct. This is the same technology that powers AirDrop. It means your devices can discover and connect to each other even when they are not on the same Wi-Fi network. No router needed. They communicate directly over Wi-Fi. Now, identity. This is where Loom gets really clever. Every device that uses Loom gets a P256 signing key pair. P256 is an elliptic curve, the same family of cryptography used in TLS and many other security protocols. This key pair is stored in the keychain, and here's the key insight. It is stored with the synchronizable flag set to true. That means the key automatically syncs across all of your devices via iCloud Keychain. So your iPhone, your Mac, and your iPad all share the same cryptographic identity. Without you ever having to set up a server or a key exchange protocol, the key ID is derived from the SHA 256 hash of the public key, which makes it deterministic and verifiable. When 2 devices connect, they perform a signed handshake. Each side sends a hello message containing a signed identity envelope. The envelope includes the P256 public key, the key ID, a timestamp, a nonce, and an ECDS signature over the canonical JSON representation. The receiving side validates all of it. Protocol version, key ID, derivation, signature verification, and replay protection. If anything fails, the connection is dropped immediately. The replay protection deserves a mention on its own. Loom includes a dedicated replay protector that validates timestamp and nonce pairs. It has a configurable clock skew tolerance, defaulting to 60 seconds, and maintains a bounded nonce cache that defaults to 4096 entries with automatic pruning. This prevents an attacker from recording a valid handshake and replaying it later to impersonate a device. Now, trust. Loom defines a protocol called Loom Trust Provider with a simple interface. You evaluate trust for a peer, and you get back one of 4 results. Trusted requires approval, denied, or unavailable. Apps can implement this however they want, but Loom ships with 2 built-in options. The first is a simple local trust store backed by user defaults. You approve a device, it gets saved, and next time it connects, it is automatically trusted. The second option is the CloudKit Trust Provider, and this is where things get really interesting. The CloudKit Trust Provider implements a layered evaluation chain with 6 levels. First, if you have configured it to require approval for all connections, it always prompts. Second, if the identity is not authenticated, meaning the handshake failed, it outright denies the connection, not just requires approval, but denies. Third, if the key ID does not match the public key derivation, denied. Fourth, if the device is in the local trust store, trusted. Fifth, and this is the elegant part, if the connecting device has the same iCloud user ID as you, it is automatically trusted. Remember that shared P256 key from iCloud Keychain? This is where it pays off. Your own devices can cryptographically prove they belong to you without any user interaction. Sixth, if the peer is a CloudKit share participant and their identity key is published in the shared zone, they are trusted. This last one is how friends and family trust works. You create a CloudKit share, invite someone, they accept, and now their devices are automatically trusted when they connect to yours. No manual approval needed. It is a beautiful system that leverages Apple's existing sharing infrastructure for cryptographic trust establishment. Let me talk about transport. Loom supports 2 transport protocols simultaneously, TCP and QUIC. When you start authenticated advertising, Loom can spin up both a TCP Bonjour listener and a QUIC direct listener at the same time, returning a port map so clients know where to connect for each protocol. The TCP path uses no delay for low latency, keep alive packets every 5 seconds, and the interactive video service class for high quality of service. The QUIC path uses Apple's NW protocol QUIC options, also with peer-to-peer enabled. Having both available means the framework can pick the best transport for the situation. On top of the raw transport, Loom adds a framing layer. The Loom frame connection is an actor that implements simple length prefixed framing. Every message gets a 4-byte big endian length prefix, and the max frame size defaults to 1 megabyte. This framing layer is what the authenticated session uses for its handshake and for stream multiplexing. Loom's authenticated session includes a full stream multiplexer. This works similarly to HTTP2. The connection initiator gets odd-numbered stream IDs. The receiver gets even-numbered IDs. Each stream is opened, sends data, and closed via JSON-encoded envelope messages. Applications can create multiple independent streams over a single authenticated connection, which is useful for separating concerns like a control channel from a data channel. Now let me talk about remote reachability, because this is where Loom goes beyond what any other Apple peer-to-peer framework offers. Most frameworks, including Apple's own Multipeer Connectivity, only work when devices are on the same local network or within Bluetooth range. Loom has a full remote access story. The relay system is a signaling service, not a traffic proxy. It does not forward your data through a server. Instead, it helps devices find each other's public IP addresses and ports so they can establish a direct connection. The relay client signs every request with both an app-level HMAC and the device's P256 identity signature. Each request includes a session ID, app ID, identity key ID, public key, timestamp, nonce, and a SHA 256 hash of the request body. The relay publishes peer candidates but never sees your actual traffic. To discover its own public address, Loom includes a stun probe implementation built from scratch. ST-STUN stands for Session Transversal Utilities for NAT. Loom sends a binding request to a stun server, by default Cloudflare's at stun.cloudflare.com, and parses the XOR mapped address from the response to learn its public IP and port. This is the same basic technique used by WebRTC and VoIP applications for NAT traversal. The connection coordinator ties it all together. It builds an ordered plan combining local discovery and relay sourced candidates, prioritizes QUIC over TCP for remote connections, and attempts connections sequentially until one succeeds. One important caveat about the relay: you need to deploy your own backend. The relay client expects a Cloudflare worker or compatible HTTP endpoint. Loom does not provide a hosted relay service. The default configuration literally points to example.invalid. This is by design. It means you own your signaling infrastructure, but it also means you need to set it up yourself. Another limitation is that there is no turn relay. S2 discover your public address, but if both devices are behind symmetric NATs that prevent direct connections, there is no fallback traffic relay. In practice, this means remote connections will work in many, but not all network configurations. For local network and peer-to-peer Wi-Fi scenarios, this is not an issue at all. Now let me cover one of the most impressive features, the bootstrap system for remote MAC access. This is what enables the remote MAC unlock capability mentioned in the announcement. The bootstrap system has three components working together. First, a Wake on LAN client that builds standard magic packets and sends them via UDP port 9 to broadcast addresses. When your Mac is asleep, the app can wake it up over the network. Second, an SSH bootstrap client built on Swift NI SSH. This handles the scenario where a Mac has File Vault enabled and needs credentials submitted before the full operating system loads. The SSH client authenticates with a password, connects, and validates credentials by running a simple probe command. It supports pinned host key fingerprints for security. Third, a bootstrap control protocol for the post-login daemon scenario. This uses a line-delimited JSON protocol over TCP, where credentials are encrypted with CHA20 poly1305 using a key derived from HKDF of a shared secret combined with a request ID, timestamp, and knots. Every request is signed with the device's P256 identity key and checked against the replay protector. The full remote unlock flow works like this. Your phone sends a Wake on LAN packet to your Mac. It waits for the Mac to boot. If File Vault is enabled, it connects via SSH and submits credentials. If the Mac has already booted past File Vault, but is at the login screen, it uses the bootstrap control protocol to submit credentials to a daemon. The whole chain is authenticated and encrypted at every step. Let me talk about LoomShell, because it is another standout feature. LoomShell provides interactive terminal sessions over the authenticated Loom transport. On macOS, it creates a real pseudo terminal using OpenT, sets up a PTY with configurable dimensions, and reads output via dispatch source on the master file descriptor. It supports STD, window resize via the TIOCS wins, Daikyo, and Cygnus, signal, and clean process termination. The shell protocol defines 9 message types: open, STDout, STDout, STDour, resize, heartbeat, exit, ready, and failure. Each message is encoded as a single byte type identifier followed by JSON for structured data or raw bytes for I/O streams. The client side provides a clean async stream of shell events. There is also an OpenSAC fallback path that uses Swift and IOSAC for a full interactive SAC client. It supports password and private key authentication across multiple key types, including ED25519, P256, P384, and P521. The system tries the native Loom transport first and falls back to SSH when direct transport is not available. Now for the media security layer. This was designed for MirageKit screen streaming, but is part of the Loom package. It uses ECDH key agreement between host and client P200 FC keys, followed by HKDF SHA 256 key derivation. The actual encryption uses CHA20 poly1305 AEA with separate nonce construction for video and audio packets. The binary media protocol defines magic numbers for different packet types and uses a compact header format. Video frames get 61-byte headers, audio gets 47 bytes. The max packet size is 1200 bytes to avoid IPv6 fragmentation. When encryption is not used, CRC32 checksums protect packet integrity. Let me talk about the CloudKit module in more depth. Loom CloudKit Manager handles the integration with Apple's cloud database. It defers container creation to an explicit initialized call to avoid launch crashes, which is a nice touch. It checks account status comprehensively, including temporary unavailability. It registers your device in a private CloudKit database and publishes your identity key ID and public key to CloudKit records. The Share Manager creates CK Share instances for peer records and provides platform-specific sharing UI. On iOS, it uses the Cloud Sharing Controller. On macOS, it uses the Sharing Service Picker. The peer provider fetches peers from both your private database and shared databases across all accepted shares. This is how the friends and family trust circle works. You share a CloudKit record with someone, they accept it, their device registers its identity key in the shared zone, and now Loom can verify their identity automatically. Let me address production readiness honestly. There are clear strengths. The architecture is clean with good separation between transport, identity trust, and application logic. The security design is thoughtful with ECDS signatures, replay protection, and AAAD encryption. Where it matters, the iCloud Keychain identity sync is genuinely clever. The code uses modern Swift 6.2 with actors, sendable conformance, and structured concurrency throughout. The diagnostic system is comprehensive with a sync-based architecture that has a fast path skip when no syncs are registered. And most importantly, this code powers MirageKit, which is a real shipping product. But there are concerns you should know about. First, while the code has been maturing inside MirageKit, the public standalone package is literally brand new. The API surface could still change. Second, this is primarily a single developer project. Ethan Lipnik is the main author, with some AI-assisted code generation. The bus factor is 1. Third, the authenticated session protocol verifies identity but does not encrypt stream content on the general purpose path. The media path has its own AEAD encryption, and the bootstrap path encrypts credentials. But if you are sending sensitive data over regular multiplex streams, you would need to add your own encryption layer on top. Fourth, the trust store uses user defaults, which is readable by other code in the same app sandbox. For high security applications, keychain storage would be more appropriate for trust records. Fifth, the quick support uses default options without TLS certificate configuration, which may limit its usefulness in some deployment scenarios. There are also some inherent limitations to be aware of. This is Apple only. It depends deeply on network.framework, Keychain, CloudKit, and AWDL. There is no cross-platform path. The relay requires you to deploy your own backend. There is no turn fallback for difficult NAT scenarios. CloudKit zone setup requires manual configuration in the CloudKit console, and the visionOS minimum target is visionOS 26, which is a future release. So who should use Loom? If you are building an Apple ecosystem app where multiple devices need to communicate, Loom could save you weeks of infrastructure work. Think about apps like shared whiteboards, collaborative tools, remote access utilities, device management dashboards, or multiplayer games that want a direct connection option. The combination of automatic discovery, cryptographic identity, iCloud-based trust, and rote reachability is something you simply cannot get from Multipeer Connectivity or from rolling your own solution on top of network.framework without significant effort. The key difference between Loom and Multipeer Connectivity is philosophical. Multipeer Connectivity gives you a session API. You invite peers, they accept, and you send data. It is simple but opaque and limited. Loom gives you networking primitives with identity, trust, and remote reach built in from the start. You have full control over the transport parameters, the trust evaluation logic, and the connection strategy. The trade-off is more complexity in exchange for more power and flexibility. If you want to try Loom, you add it to your Swift package manifest pointing to the GitHub repository. You create a Loom node with a service configuration, call Start Advertising to begin broadcasting your presence, use Make Discovery to browse for peers, and create sessions for peer communication. The API surface is clean and well documented with doc-C tutorials and articles for all major flows. My recommendation, if you are prototyping or building an internal tool, Loom is ready to use today. If you are shipping a consumer app, I would keep an eye on it, but wait for the API to stabilize and for the community to grow a bit. The foundation is solid because it comes from production code, but the public package needs time to mature. Start the repo, follow the development, and start experimenting. The networking problems Loom solves are real and painful, and having a well-designed open source solution for the Apple ecosystem is genuinely exciting. Check out the project on GitHub if you want to dig into the source code yourself. The architecture is clean and the code is well organized, so it is a great learning resource even if you do not end up using the framework directly. And that is Loom